Today we are going to do arc length and curvature, which is section 3.3 on page 283. Now the arc length, it has always been defined, I think in calculus 1 even, as x prime squared plus y prime squared. Take the square root and you integrate from one to the other point, and that's your arc length, which is given by your book on this page. That's the 2D. Okay, a 2D curve. What if we had a 3D curve? Nothing changes if it becomes 3D. Everything follows exactly the same, except you have a third item to square and then add the square root. So instead of f prime plus g prime all squared and stuff, you get f prime, g prime, and h prime all squared, and then you take the square root. But the principle is exactly the same. So then, but at this point, however, I should mention that when let's look at the theorem 3.4 at the bottom. All right. Now so far we have defined that r of t, that is our vector function, which we call r, is defined as f of ti plus g of tj. All right. So the arc length of this curve r is going to be given with a familiar function, but we can also look at it as the integral as the absolute value of r prime, because r prime is f prime t and g prime t, and with the I and j included, of course. So then the magnitude of r prime is exactly with that, the integrand in the arc length formula. That's why it all works out. And that's of course true if it's 3D as well. With 3D, that is, if your r is fti plus gtj plus htk, then the s will be equal to the integral, basically the same as the integral of r prime t in magnitude, and then you integrate it from your one limit to the next of t. And that would be how to calculate arc length. Now, having said that, first, let's do an example. Arc length is kind of a pain, okay? But this example has made it somewhat easier. In general, I'd say this: unless the arc length, it looks very simple to do, let's use the definite integral calculator and not do any tables or the integration by parts. Let's not do that. We've been there, we've done that. We don't have to do that right now. Okay, so please do example 3.9 as part of your homework. Next, let's look at some helix. A helix has the form, please look at page 285, where they give you the form of helix. A helix basically is the cosine some number of t, and then sine some number of t, and plus some t, okay, multiplied by some number. And that would give you some kind of helix. Of course, that's the ijk coordinates, but they can be interchanged. For example, cosine can be with k, and sine can be with I, and t can be with j, etc. Then your helix just, goes some other way, but it's still a helix. The point is, the formula for helix, your book has worked it out to be that thing down there, which might look like easier, but it really isn't, because then you have to turn your helix into their form. You have to know what r is, what n is, what h is, and then beat around in there, and by the time you're done, you might as well just calculate the arc length formula, which in this case isn't so hard because you have sine squared plus cosine squared in there, as you can see, and that just turns into 1. So calculating the arc length of a helix is, you don't really need this formula. It's probably faster if you just, use the general standard arc length formula and crank it out, because the sine and cosine will disappear, making everything much better. Well, somewhat better anyway. So, well, in some cases. So that's just something I want to mention quickly about the helix. But let's move on to arc length parameterization, which means you make arc length into the parameter. Normally, when we talk about vectors, we use t as the vector. T is just some random variable that we use as a parameter, right? But if you use s as the parameter, then because s and t has some kind of a relationship, so if you figure out what that is, is then you can solve t in terms of s and plug it into the original vector function such that your vector now is, instead of r of t, it becomes r of s. The benefit of doing that is that s is t. You don't know what t is. Okay, t is just some random number that makes your curve go. Whereas s is, you know what s is. S is the distance on the length of the curve. So as you can see, for the right amount of s, how your vector is moving. So in some ways, it's better. So that's the whole point of doing this thing called the arc length parameterization. Okay, and so then how do you calculate that? So we start with s of the definition of s of t, and which is the bunch of stuff squared and then take the square root thereof, right here, and that's the first one on this page. And well, you can just look at your book, of course. Then the next step is we're going to take the derivative s prime of t. And notice s prime of t, by the fundamental theorem of calculus, is r prime of t, the absolute value of r prime of t, where r is your original curve, vector curve. Now then, as a result, then sometimes that might help you in calculating what s is in terms of t. But being that there's a square root, that might not come easy. Okay, so let's go to the next page, where the theorem sums that information up. That is, on the next page, 286, it says that s of t will be an integral from a to t. A is the starting point, usually 0, but doesn't have to be. So integral of a to t of the absolute value of r prime. So and furthermore, being that it is the integral of the magnitude of something, ds by dt, which is r prime of t in magnitude, is always going to be bigger than 0, with certain minor conditions. Yes, and so, and anyways, now to see what this is all talking about, let's look at examples 3.10, part A. This is on page 286, where you have r of t equal to 4 cosine ti plus 4 sine tj. Now what is that? If you see something called cosine t and then sine t, that's a circle, okay? And so, but never mind that it's a circle. The point is, when you apply s of t's formula as we define it, you find out that this whole thing integrates conveniently, such that s of t is just 4t. In other words, s equals to 4t, which means t is s over 4. See? As it says right down here. So you have a short, simple representation of t in terms of s. Now when that happens, you can plug t in terms of s into the original formula for r and get a different representation of r. So r now, instead of t, now is represented in terms of s. And this is called the arc length parameterization. Okay, and then you have to remember that before, the t was given some restriction as t bigger than or equal to 0. And being that t is s over 4, then you can figure out that s also has to be bigger than or equal to 0. And that's all you have to think about. So, so please do example 3.10, both part A and B, as part of your homework to get a feel for the arc length and parameterization or something business. Next, let's look at page 288, curvature. A curvature is defined as dt by ds, okay? Whereas t is your tangent vector, and then whereas s is the arc length. The curvature means that how sharp of a turn it is. See, this is a very sharp turn. That's your car, and that has so it has a lot of curvature, okay? And whereas this is a slow turn, so it has not much curvature. So basically, the sharper the turn is, the more curvature there is. And if you have a straight line, you got no curvature at all, okay? Slight bend, slight curvature. So that is the meaning of curvature, but being that this is very hard to do because the arc length parameterized something station or something we just did is very hard to do most of the time. So what we're going to do is find some other way of calculating the curvature. And we're going to prove that curvature is the same as t prime of t over r prime of t, where t is the tangent vector of r. Now, having said that, before we start doing the proof, I want to refresh your memory on various theorems that we have learned so far in no particular order. Really, these are all screenshots I got from your book. Okay, now please look at this. That the first one, the property, this is from theorem 3.3. All right. Okay. Now, as you pay attention to ones that are marked with red, the scalar product. The scalar product means when you take the derivative of a scalar function with a vector function, it works exactly like a regular product rule for derivatives, right? You just take the product rule as like you normally do. Similar to cross product, when you take the derivative of the cross product of two vectors, you do it the same way. Take the derivative of the first one, cross the second, then the derivative, then the first one cross the derivative of the second. That is, each one gets taken derivative once, but their order does not change. Okay, you can't flip them around because the cross product is not commutative. So you can't go first. You have to go second the whole time. Other than that, everything follows. And rule 6 there, let me see if I can turn this thing. Anyway, where it says the derivative of the vector of a function, right, where f of t is on the inside, you just do the chain rule like you always do. You take the derivative and then take the derivative what's inside. And then lastly, this is important to remember, if a vector dot itself, this is the dot product, if a vector dot itself equals to some constant, then the vector is perpendicular to its derivative. Okay, this is important, and we already proved that, both in the example and even in one of the homework, right? So that should remember all this for the coming proof, okay? And next, the property of the dot product. I just want you to remember where I marked the red part, which is any vector dotting itself is the same as its magnitude squared, okay? And that's all. Next, the something we just mentioned, theorem 3.5, which states that the ds by dt that we just defined, right, is equal to r prime of t, yeah, okay, which is bigger than 0 all the time because r prime of t is calculating its magnitude. So that's why it's always positive. Next, theorem 2.6, that's way back a while ago, property of the cross product, where we learned that, look at the one that marked with red, is v cross v equal to 0. That is, a vector crossing itself is always 0. That's because the cross product is the magnitude of the parallelogram that the two vectors make. And the two vectors are the same vector, there's no parallelogram to talk of. And finally, the magnitude of the cross product. Here's a formula, yeah, like I just mentioned, right? The magnitude of the cross product is uv sine theta. Okay, it's just one thing we did at some point ago, page 170, yeah. And so, having refreshed all that memory, so let's now proceed to prove this thing. So to prove this theorem, first we start with the chain rule. By the chain rule, then dt big T by the tangent, that is, dt equals to dt by ds by dt. So here's the chain rule that we mentioned a little bit earlier in the reminders. Okay, this is written slightly differently, but it's the same concept. So here's our chain rule, and then we divide both sides by ds by dt. Then we get dt by ds will equal to this thing divided by that. Okay, so it be equal to dt by dt, big T by small t, and then ds by dt. And the magnitude, of course, are the same as well. So we stick the magnitude in there. And what does that equal to? And this is the definition of kappa, by the way. This little k pronounced kappa, which stands for curvature. And so this is the kappa. But what is that? Then the big T by dt is T prime. Okay, so this is T prime of T, and then this is equal to T prime of T, this one. And ds by dt, as we mentioned earlier, is equal to R prime of T. That is one of the things we reviewed a little bit a moment ago. So that's why the first part of formula is proven. All right, so next. Now at this point, we need to go forward to a few pages to page 292 because the proof for this requires that we mention the normal vector. But the book forgot that we haven't had to cover the normal vector yet. That is a couple of pages later on page 292. So please flip over so we figure out what is the normal vector. Okay, the normal vector, as you might imagine, is defined as the derivative of the tangent vector T prime of T divided by its magnitude, because the normal vector is a unit vector. And then the next thing we are going to define is called the binormal vector, which is the cross product of T cross N. So you have all these vectors. Now these other stuff might sound a little bit confusing. Just keep track of them carefully. Okay. First, remember what T is. Before you forget what we're doing, T is the tangent vector and is defined as R prime of T divided by its magnitude. Okay, so T is taking one derivative, and the unit normal vector is T prime of T divided by its magnitude, and that means it's basically the second derivative. Okay, and being that it divides by its magnitude, normal vector is also a unit vector. And also you notice T prime is parallel to N. That matters later. Okay, and being that it's defined by T. N and T prime are the same vector, except they got normalized. So remember they are kind of the same thing. Although this might be difficult to remember because we're looking at a lot of tiny little formulas at the same time. But try to keep track of it by writing a note or something so you can look it up, which one is what, and things like that. So then we have certain qualities. First, we need to prove that the reason it's called the normal vector is that the normal vector is perpendicular to the tangent vector. Now, how do we know that? The proof of it would be that, let's take T dot n, okay? That would be T dot T prime divided by some scalar, right? And we need to prove that that's zero, because if it's zero, always zero, then it means they're orthogonal or perpendicular. Now, so what we're going to do is that consider T dot T. Okay, I have it scratched out. Now, what happens when you have T dot T? A vector dot itself is its magnitude squared, as we saw a few minutes earlier in the reminder. Which means so then, being that T is a normal vector, is a unit vector, its magnitude is always 1. So T dot T is a constant, which by theorem 3.3, the last theorem that we also mentioned a few minutes earlier, if a vector dot itself is constant, then the vector dot its derivative is 0. Okay, on page 272, I mentioned again here. Therefore, T dot T prime is 0. But n, as you notice, n is made out of T prime. Okay, it's just a unit vector for T prime, which means T dot n equals to 0. And therefore, T and n are orthogonal. So remember that n is parallel to T prime, and n is orthogonal to T. So that's one thing. Being that we're here, we might as well finish the binomial vector as well. Now, binomial vector is defined as T cross n, which we can prove quickly that the binomial vector, by its definition, is going to be perpendicular to both T and n. How do we know? And well, that's just because it's a cross product. Cross products, the result is all by the right-hand rule. Okay, it's always perpendicular to the original two vectors that you're crossing. However, the binomial vector is also a unit vector, and we can prove that by noting that by the definition, one of the definition or magnitude or something of the cross product, the cross product equals to the magnitude of the two products times sine theta. In this case, since t and n are orthogonal, meaning perpendicular, we showed it right up here. Okay, this side. Okay, so which means that the angle between them is 90 degrees, pi over 2. And therefore, sine theta equal to 1, and therefore BT's magnitude is the same as t times n's magnitude, and they're both 1, so BT is also 1. So that marks the end of the normal vector, and now we'll continue to prove this thing right here. Let's go back and prove it. But before I finish, I want to repeat this point that we proved earlier, that t dot t prime is 0. That is, which is why t and n are orthogonal, because n is a unit vector for t prime. But generally speaking, t and t prime is orthogonal, and I will write it down here because we'll need that for our proof. T prime is orthogonal. Okay, that will mean we'll use that thing to mean orthogonal. So having said that, let's keep going for this proof. Now, first, this is for a three-dimensional proof because we have the cross product. The cross product is in the third dimension. If you don't have a three-dimensional curve, there's nothing to cross, okay? Because it's not going to get out of there. It only has 2 dimensions. It's stuck in the 2 dimensions. So with a three-dimension curve, we will have we will go back and doing all the stuff. Let's rewrite everything. I'm now back on page 289 and continuing our proof of that thing. Okay. Now, so we'll write all this stuff down. So t of we didn't write this down. So t, which is the unit tangent vector, is defined as r prime t, r prime divided by its magnitude. Okay. R of prime of t. Okay. That's the unit tangent vector. And ds by dt is, as we have mentioned a little bit earlier, right here, ds by dt is r prime of t. That's also mentioned a few minutes ago, is r prime of t, the magnitude of r prime of t. And now we're going to, therefore, we're going to do something like rewrite stuff. So we'll plug that in here, okay? Because that, well, it doesn't matter how many absolute value signs I use, they're the same thing. And to me, anyway. So we're going to plug this in here, and we get r prime of t equals to t, big T of t, that's the unit vector, divided by times something, times ds by dt, which is this thing, which is, okay. Right? Yeah, so it's this thing times that equals to this, because ds by dt is the denominator. All right, so far so good. And then we are going to do our double prime. Now recall the derivatives of vectors. That means you can take derivatives nicely and in order, and everything works out just like if it's a normal non-vector, a scalar function, right? So we'll do this derivative then becomes, we'll write this thing in front like the book does. So it becomes d squared s ds squared, sorry, dt squared. Well, that is a horrible erasing job. So ds squared, so we'll take the derivative of this thing, keep this thing intact, plus the, we'll write this thing down first. Now this is just a scalar multiplication, so it doesn't matter which order we write it, but we'll still follow the plan just to be consistent. So we get that, and that's applying the product rule for vectors and scalar function. So we got that, and then we're going to do, okay, next we are going to take this thing, cross this thing, okay, because we're trying to do that in our proof. So when you cross it, what you get is a bunch of writing. I will skip some of the writing, and we'll just look at the book. What you get when you cross it, then you end up with crossing each one, right? As the formula goes, when you do cross product, you can cross each one in order, as long as you do it in order, and everything works out okay. So when you do that, then you notice the first cross product has t cross t. That is, t is crossing itself. Now, as we mentioned a few minutes ago, t cross t equals to 0. Anything cross itself is 0. So then we only have the second part left, which I will write it down here. So that makes it a little less writing for me. So we'll write that down. So that equals to ds by dt squared. And then we have t cross t prime. All right. Now the next thing, we know that t and t prime are orthogonal. Okay, I said it right here. T and t prime is perpendicular, as we proved a few minutes ago. That means the cross product then equals to the angle between them is 90 degrees. So whereas the magnitude of t is just 1, I just show it to you like this. Now the magnitude of t itself, being the unit vector, is just 1. There's the formula for the cross product's magnitude, right? It times sine of the angle. They're orthogonal, so the sine of angle is 90 degrees. So what you have left is just the magnitude of t prime. And therefore, we have this equals to the cross product then. Now for the next line, your book forgot to slap on the magnitude. That's why there's a magnitude on this side and your book forgot the magnitude on this side. So please add the magnitude for that line. It just means that the magnitude then, it will be equal to here because we are trying to prove something related to the magnitude. So now we're getting very close to the answer because what is ds by dt again? ds by dt is r prime of t. See? So then what we have is t prime divided by, what I mean is that at this point, then we will isolate t prime there, okay, put this thing on the bottom of the equation, right? You have ds by dt squared, and then we're very close now. Now we have just t prime, this equation right here, right? We are looking for kappa. If t prime equals to this thing, and this part is actually r prime of t, ds by dt right here, see? ds by dt is equal to r prime of t magnitude, right? So then if you take, so then kappa is defined as t prime divided by one more of this r prime of t. So there's a squared here. So you have the 3 of them. So you're dividing all 3 of them, and that proves that the equation that kappa equals to r prime cross our double prime and divided by ds by dt or r prime t 3 times, okay? And that is the equation, which is given right here, and that's what we've been trying to prove. See, right here, this in the middle of the page of your book. And that's how you got here. As you notice that this proof required us to remember a whole lot of various things that we learned in the last chapter or so, maybe 2. And so it's an excellent proof to go over. See, it forces you to remember which is what is why, all those things. Okay, so one more thing we have to prove for this theorem. What is the last thing again? That is, now if C is a graph of function, the last part is we come up with a simple equation for a 2-dimensional function to calculate the curvature, which means if y equals to f of x, what is the curvature? What we're going to do is we're going to use the curvature formula that we just derived, fresh from the oven, right here, right? And we're going to turn this function into a 3D function basically. So we'll define r of t equals to xi plus f of xj plus k, 0k. So that would be our same function, but we stuck it in the 3D for no reason. Actually, there's a good reason for it, as you can see. And as a result of that, what we have is then, so then we follow this formula up here and plug it in. So what is our prime of t is that, our double prime of t is that, and to do the cross product, very quickly you'll notice that the cross product, due to the abundance of zeros there, end up being f double prime x of k. And then kappa will be equal to all the stuff, okay? So it's f double prime of x, right, on top, that's the cross product. And then r prime, which is the first one. And the magnitude of that is 1 plus f prime of x squared, take the square root, and then cubed, okay? So that's what you get down here. It all follows from the equation that we just worked on. That was fairly complicated, actually, and nicely used all the formulas we've learned and make us remember all that stuff. All right, so now that we have proved the formulas, to apply is actually very straightforward and might be tedious as well. So please do the next example, which is example 3.11, which is talking about, the first one talk about the curvature of a helix, which I think is, well, I think they're all fairly complicated, but straightforward, okay? And then when I say complicated, I'm talking about tedious. You follow the formula and crank out a whole bunch of stuff, as you can see. Flip the page, there's more stuff. Anyway, if you get out all that algebra alive, then you come up with the answer for what? What is this, part B? Where the answer is just 1/2. Okay, so that is that. And now that we have finished proving this stuff, I want to mention what the curvature really is by showing you the curvature of a circle. The curvature of a circle is constant, which means curvature is a quality of circles, okay? Each circle has its own set curvature. And let's look at this. Now let's consider the curvature of some circle. Okay, a circle is normally in vector form is represented by r of t equals to r cosine t and r sine t. Now the big R stands for the radius, and the small r is the vector function. I guess that's just the tradition that we use the small r as the vector. So to calculate the curvature of a circle, we'll apply this formula right here, okay? So then what is the r prime t is equal to r prime t, which we need to calculate t, okay, because t is r prime. So r prime t is, let's see, r minus sine t, all right? And then our cosine t, all right, and in which the absolute value of r prime t is equal to r. I don't know that this matters, but we'll write it down, I guess. Okay, so then, and then secondly, so then the t then, the unit tangent vector, which is r prime of t over absolute value or something. No, I think, no, it doesn't have absolute value on top, only bottom. So equals to r prime t over divided by r itself, divided by the magnitude, okay, which is r, and which is equal to equal to minus sine t cosine t. And as you can see, that's a unit vector. And we're only talking about a circle in 2D right now, I think, yeah. And anyway, so then t prime, you keep cranking this stuff, and that equals to minus cosine, right? Minus t prime would be minus cosine t minus sine t. Okay, so far so good. And then whereas the magnitude of this thing of t prime is equal to 1. All right, so then we crank out the formula of t prime over r prime. So the kappa for our circle equals to t prime, which is the absolute value of t prime, which is 1. Kappa equals to t prime over r prime, right here. See, I'll even rewrite this thing, over r prime, which is equal, t prime is 1, we said so right here, and then r prime is r, we said so right here, okay? And so as you can see, the curvature of a circle is the inverse, the reciprocal, that is the reciprocal of its radius. That is, the bigger and fatter the circle is, the smaller the curvature is. The smaller circles has much bigger curvature. The reciprocal relationship, and that gives you a direct understanding of what curvature is. In other words, if you have a curve, right, going around, and maybe have a sharp bend or something. Anyway, so right here, when it's close to it, if it's continuous and stuff, so that the curvature here is very in the small neighborhood is very similar to the circle of its curvature. Say if the curvature is 1 over r, then you just draw the circle at that point of the circle that has radius r, right? And that circle will, that part of the curve will simulate the circle in that short amount. That is like part of that circle has identical or almost identical curvature. And there's a name for this. It's called osculating or something like that. But we'll talk about that in a second. Okay, and that gives you a complete concept of what curvature means. Is the quality of a circle, is 1 over the radius of a circle, and it's constant for each circle. Okay, so having said that, let's turn the page. We have covered the normal and binomial vectors, so turn the page a little more and look at the examples for normal and binomial vectors with and the principal unit normal vector and the binomial vector. Yes, example 3.12. Please do that. Whoa, it seems to go on for some reason. Whatever, please do that example as part of your homework. What is this again? Example 3.12. So you have to figure out what t is, and then figure out what n is, then figure out t dot n, which all look like quite a bit of work. So yeah, so it's good for you to do it, okay? And doing it once and then finding the binomial. You wouldn't think it's that hard, but apparently it is. And anyways, yeah, so if you plow through all that algebra and if you come out not making a single mistake, then you should be able to find the right answer. All right, so next, I'm now at page 297. Let's look at what happens with the t and n's and tn and, of course, b. Okay, the three vectors, what do they do? And I made a little model to show you. Okay, here's my little model. Now this is my curve in space. Okay, I made it out of aluminum wires. They are designed for making crafts. Some people are talented and can make crafts out of this stuff. I can't. Anyway, and then I made this thing, which is 3 directions. Okay, this is t. Okay, you can see it. And then this is n. Well, where's n? Up here. And then remember, tn, the cross product of t and n. Okay, cross it with your right hand from t to n, okay, gives you b, see? So my orientation is correct. And then, so what you do is you take this thing that, use t is the tangent, so t follows the curve, okay? And then n and b just sort of come for the ride. Now n is determined by t, but n is like the second derivative. So where it goes is kind of hard to say just by the path of the curve. So it depends on t. So it might go, I don't know, it goes this way and that way depending on what t is and how the derivative works. So you just keep going, see? And t and n might move around, who knows? I mean, n and b might move around, but t will follow the path. Okay, t is the only thing that follow the space path and keep going like that. See, you can. This is a neat little way of seeing how the 3 vectors work. So that's that. And let's see next. What do I say? Oh yeah. So what happens is then there are different planes that's defined by these things. Let's look at the next page. We are now on page 298, where we're thinking about the osculating circle. That's the circle I drew earlier. Okay, where you find the curvature, then the curvature is 1 over r, and you can draw a circle right there, and that is your osculating circle. Excuse me. And example 3.13 helps you calculate the equation of that circle, which is I guess okay, but I think I'm missing something. Where's my Okay, please do example 3.13 as part of your homework as I figure out where did the osculating planes go. Let me find it. Okay, I found my planes. It's on page 297. See, there are two planes to think of. First, the normal and the binormal vectors, these two things. Let's see, what am I looking at? Okay, over here is good. Okay, normal and binormal. And here's a tangent, which is going along the curve, right? The normal and binormal forms so-called a normal plane because it's perpendicular to the curve at that point. And then the tangent and the normal forms what's called the osculating plane. That is, that's the plane where that circle sits, I guess. And that, yeah. And in your homework, you'll be asked to calculate either plane or both. And that's what they are, is you have a plane that's perpendicular and a plane that's along the tangent. And the normal, okay? Tangent and normal to form, so you got two planes and each point of your space curve as you go along. So let's see. So for homework, let me see. That's the end of this section. So for homework, please do on page 301 problems. Problems 107, 111, 115, 19, 25, 27. 27, it doesn't say, so please assume that t starts at 0. Okay, it matters for the answer, but to match the answer at the back of the book, t starts at 0 is a good idea. And next, 131, where answering in the back is a little bit wrong, I understand. 135, 39, 141, answer in the back is missing y. And then finally 147. And then yeah, and I will talk. Please go do your homework, and in the next video I will talk about them.